Hello everybody and welcome to another Java video. Today's lesson we're going to talk about algorithmic recursion. And it's going to take us a couple lessons to get through all of the nuances for how to use recursion. First understanding what it is and then how to use it in a nuanced fashion. Today we're just going to talk about the basics, which is you've probably heard about recursion, but what exactly is it and how would we use it to solve a problem? So the first thing we're going to look at is a definition. So recursion is a technique or an algorithm that calls or refers back to itself. So the best way to think about it is like a method. If you write a method and that method calls itself, then what you are doing is implementing recursion. Now there is a second part to recursion, and that is that it can't just call itself indefinitely. What it needs is to have some sort of a base case or a stopping point. So if you're calling a method and you're giving it a parameter like 5, you're not going to continue giving it 5 and 5 and 5 forever. At some point, something needs to change. So usually when you implement recursion practically, when you call itself, something is changing, and that's usually found in the parameters, where you're somehow changing the parameters every iteration or every time you are referring to yourself. I'm going to give you a bunch of examples to help this. But that first piece is self-referral. And the best way to think about this would be to think of a Santa. Okay? And here I have a Santa. And this Santa may look like a Santa, but it's a method. And within this method, I can call myself. And what I have is another. But this, you'll notice, is slightly different. Maybe it was given different parameters, and so it's the same method, but it's going to behave a little bit differently. But it's still going to call itself. And so now that method calls itself. Different parameters, behaves a little bit differently. That method calls itself, different parameters, behaves a little differently. That method calls itself, maybe. And then we finally reach a point where it is not going to call itself anymore. And that piece is what we refer to as the base case. You recurse, you recurse, you recurse, you recurse. At some point you reach the base case and there is no calling itself from that base case. And so if you want to think about it like a for loop ends, right? It has a starting point, it has an ending point. A while loop, the same idea. It's not going to loop forever. It's going to loop until that condition is not met. Well, a recursive algorithm is going to have some sort of a condition, usually an if statement, which is going to say, if I've reached this base condition, if I've reached the tiniest little piece that I can, I'm not going to keep trying to go any further. I'm going to stop. And so it usually represents some sort of a lower bound. Now, keep in mind the way that methods work is that when I get to that base case, that method is going to return. And when that method returns, it's going to return to the place that called it. And then that method is going to finish whatever work it has to do, and it's going to go back to the method that called it. Oops. And then microphone troubles aside, that one is also going to go into the place that called it, which is going to go back to the place that called it until it finally gets back to the original spot or your main method or wherever that might be. And that is sort of the end of the recursion. So I want to show you this in a couple of different ways, but first I want to show you a simple example of recursion. It doesn't do anything exciting. So here I have a simple method, which you're familiar with. How do we know that this is a recursive method? Well, we scan the method and I can see inside it I am calling myself. So this method, my method, is calling itself. Now remember, one of the keys here is that something has to change with each call. or else we're never going to get to that base case. And so in this case, what's happening is it starts off at x, let's say it's 5. Then it's going to call the method with 4. And then it's going to come back up here. And then it's going to call the method at 3. And then it's going to go back and call the method at 2. Then it's going to go back and call the method at 1. Then it's going to go back and call the method at 0. When it gets to 0, it has reached its base case, and it is actually going to return the value of 0 back to the method that calls it. So in other words, this is going to return a 0, which is going to be added to the return value. Okay, that makes it 0. But then when this returns, it's going to take the 0 and then add it. And then it's going to add it, and then it's going to add it, and then it's going to add it. And it's going to keep adding and adding and adding to the return value until it finally actually returns. And that is a really dumb example of a recursive algorithm. So in general, anytime you're asked to create a recursive algorithm, you're kind of following the same pattern. You're going to do some work, maybe. You're going to have some sort of an if statement for the base case. And then you are going to have the recursive piece to it. And you have to have those elements in order to have a proper recursive algorithm. So most recursive algorithms that we're going to deal with are going to be algorithms that have some sort of parameter. And I told you why, because something has to change from iteration to iteration. And the second thing is it usually has a single value that's going to be returned. And that's just because it could have multiple values that it's returning. But for what we're going to be considering at this level, it's going to be just single input, single output. So let's look at an example. Powers. So you all know what a power is, 2 to the power of 3. If you think about how you learn powers, 2 to the power of 3 was 2 times 2 times 2. Or 2 times 2 to the power of 2. And 2 to the power of 2 can be written as 2 times 2 to the power of 1. And 2 to the power of 1 could be written as 2 times 2 to the power of 0. So thinking about that, how would you write x to the power of y recursively? And anytime you're asked to do something recursively, you have two things that you need to think. You need to think, what's my base case going to be? And you have to think, what is my recursion going to be? How's my parameter going to change from round to round to round? So in this case, with powers, what is the base case? Is it to the power of 1? Not to the power of 1, because that answer is different depending on what the base is, right? 3 to the power of 1 is different than 2 to the power of 1. So what your base case is in this case is the power of 0. Everything to the power of 0 is 1, right? So that's a base case. Now, how does recursion work? Well, if you think of the example I gave you, 2 to the power of 3 can be written as 2 times 2 to the power of 2. That's still doing a power, but it's now reduced itself a little bit. And so that is what we are doing here. So yes, it is recursive, because I can rewrite something to a large power as something to a smaller power. That's sort of the definition of recursive. And it does have a base case. Anything to the power of 0 is 1. So that means that I can definitely do this. So there's my method. It's going to have 2 simple inputs. It's going to have 1 simple output. And the process is going to be, if y equals 0, return 1. Nice and simple. Otherwise, you're going to return x times, and then the recursive part, the power of x minus x comma y minus 1. That's it. There's nothing else you need to do in order to compute it. And this will return the correct answer. Now I want you to look at this in a slightly different way, because it's important to understand what's happening here. What's being built is a tree, a path that the computer is going to follow. The power 4 to the power of 5 can be written as 4 times 4 to the power of 4, which can be rewritten as 4 times 4 to the power of 3, and so on until we get to the base case. And so what the computer is doing is it's building a path that it follows. And it's going to keep going. It's not going to do any of these evaluations until it reaches the bottom, the base case. And then from that base case, it is going to go all the way back up this tree to the very top point. So in other words, it doesn't do any multiplication, nothing. It comes here, it has an answer of 1, which it sends back to here, which becomes 4 times 1, which is 4, which comes back down to here, which becomes 4 times 4, and 4 times 4 times 4, and so on until it gets back to the beginning and gives you your proper answer. So it is literally building your answer from the ground up. Now this is a simple linear path, but I called it a tree. And the reason I called it a tree is because it is possible to call the method multiple times within itself. And so it could be that you have 2 or 3 or 4 branches coming from each spot. So recursion is one of those things where the best way to learn it is to practice, and not to practice programming at first, but to actually practice the mental games of how to turn a problem into a recursive problem, how to solve it recursively. And there are a number of examples of that, and if you're following along in my course, you're going to actually be doing these together in groups. One of them is the very famous problem called the Towers of Hanoi. It's a game. I mentioned my my kids make games, and this is one of the things they make at Cheshire is the Towers of Hanoi puzzle. And the way that the Towers of Hanoi works is that you have a number of towers, and you need to get the towers from one peg to the other peg, as so. But the rule is that you can only do it by moving one tower at a time. That's rule number 1. And rule number 2 is that you cannot have a larger tower on top of a smaller tower. It's not allowed. And so there are lots of ways to solve this puzzle. And so you can start to think of, moving around and trial and error and figuring it out. But this is an example of a recursive puzzle. And remember, the rules for recursion is, can you take a problem and can you break it down into a similar but smaller problem? And then the second thing you need to consider is, what is the base case? What is the point where you just know what to do and you just do it? So that's something I'm going to leave for you to think about. Fibonacci is another very famous sequence, which is a recursive sequence. So I'll get you to kind of read that and think about it. Factorials. So factorials are a concept you should have covered in math, which is looking at how you can redefine 3 factorial as being 3 times 2 times 1. And so how would that fit as a recursive algorithm? We've looked at binary search and binary searching, and you've actually written the algorithm for binary search. Well, that algorithm could be rewritten as a recursive algorithm. Think about how that might be possible. The last one is another famous problem, which is toads and frogs. The idea being that you have to get all of these onto the other side and all of these onto this side. And again, with very simple rules. You can only slide these ones in this direction and these ones in that direction only, or you can hop over one other piece. So in other words, if I move this here, I'd be deadlocked because I can't move anything anymore. If I move this over here, I can hop in this direction. I could slide this over this way. I could hop over in this direction, but now I'm deadlocked again. And so it turns out that this also has a recursive solution, because even though I've only put 2 pieces on each side, you could take that solution and you could expand it so that there are multiple. You could have 4, you could have 8, you could have 1,000 on each side of the puzzle. And if you have a good recursive solution, it will be able to solve that regardless of how many you have. Then the last problem that you might want to consider is the greatest common denominator. And that's sort of a bit of a bonus problem because it can be a little trickier to think through. So for today's lesson, that's the important concept I want you to get. I want you to work on some of these problems here. I'll put them back up here. I want you to work on some of these problems here to get your mind used to thinking about recursion. Our next lesson, we're going to focus more on the programming side of things. What are some of the gotchas? What's actually happening? We're going to talk about stacks and things like that. So for now, enjoy these problems and see you next time.